Hello and welcome to OpenRelay Screenside Chats Episode 6. Today we're going to be talking about the internals of OpenRelay's Widget Toolkit. So for a high-level overview, you'll want to go back to Screenside Chats Episode 5.5 for an introduction. There we introduced the widgets that I had written as of 2 weeks ago and gave a brief walkthrough of how they can be used, not how they work internally. Today, we're going to be taking a look at the core elements of the Widget Toolkit, looking at the base classes that can be used to build new elements, how templating works within these elements, data binding, logic, and the various events that get passed between the different elements. So to start with, we have the Web3 tag, and we talked about this on the last episode of Screenside Chats, but it has evolved a little bit over the intervening 2 weeks. So essentially, we have the OR Web3 tag, then we have the content that shows if Web3 is available. And this right here, I just show this as plain text, but this could be arbitrarily complex HTML. Part of the idea is that this may well be most of your application that built within the OR Web3 tag. Then we have the no Web3 slot. So this is an element that is going to be shown instead of the core element if Web3 is not available on the user's machine. So we're showing this as a span tag, but it could be a div tag or any of a number of other kinds of tags, and the same is true with each of the tags here. The important thing is that they say slot equals and match the slot names that the OR Web3 tag expects. So here, if I did not have Web3 enabled on my browser, this would say, this shows if you do not have Web3. If my Web3 client were locked, it would say, this shows if your Web3 plugin is locked. Down here, I say that this DApp supports network 1, so that means mainnet. If I were connected to, say, Kovan or Ropsten, it would display the net unsupported slot that says this shows if your DApp does not support the current network. So this gives you an opportunity as a DApp developer to, without having to write any JavaScript at all, have the core of your DApp that shows for users who are have everything and ready to go. You can just show the DApp. If they don't have Web3, you can have a section that explains how to get what they need. If they have Web3 but it's locked, you can give them simple instructions on how to unlock Web3. And if they're connected to the wrong network or a network that you don't support, you can give them instructions on how to change network. So it makes it all very simple. There's no JavaScript programming involved, just to do a simple DApp that detects Web3 and shows users what they need to know. Some various features of the OR Web3 tag. So you can, as we just talked about, select content based on the Web3 status. It also manages Web3 injection for the child elements. So rather than each element that we implement needing to figure out where they're supposed to get Web3, they're nested underneath a Web3 tag, and they get Web3 from the ancestor Web3 tag in their DOM. The Web3 tag will monitor for account changes. So if the user goes into, say, MetaMask and switches from one account to another, the Web3 tag is monitoring for that and will automatically apply those changes. It monitors for network changes. So if they were connected to mainnet and switched over to Kovan, it will notice that and make the proper changes. It will also monitor for new blocks if any of the child events have indicated that they need new blocks. And we'll talk about why that's powerful a little later on. As it monitors for these changes, it will emit those events to the child elements so that they get those notifications automatically without having to do anything within their code to monitor for them. But by monitoring for these things that are fairly common at the Web3 tag level, the individual tags don't need to worry about proactively monitoring for these things, which means that's less code executing, potentially less RPC calls executing to find out who am I logged in as. If each of the elements had to handle that individually, that would be a lot of repeated work that can all be handled in one place with the Web3 tag. So there are several events, Web3 related events, that the Web3 tag watches for. The first is the Web3 child event. So this event is emitted by child elements when they are added to the DOM. So when a child of the Web3 element is inserted into the DOM, it will emit a Web3 child event, which bubbles up the DOM and gets caught by the Web3 tag, which then adds that child to a list of children that will be notified when those other events happen. There's also a set Web3 event, which can be triggered by the application. Either it could be done through jQuery or React or Angular or whatever your application framework is. It can find this Web3 tag and set Web3 explicitly. So by default, the Web3 tag will look for a window.web3 object that gets injected by something like MetaMask. But if for your particular application you want more control over it than that, and you don't want to just rely on injected Web3, you can still use the Web3 tag and explicitly inject Web3 through your application. The last event that it watches for is a subscribed block. So if a child wants to know about new blocks as they happen, it can emit a subscribe block event, which will bubble up through the DOM, get picked up by the Web3 tag, and then as new blocks happen, the Web3 tag will notify each of the children that have subscribed to blocks that a new block has just occurred. And then Web3 events. This dispatches events down to children. And I should maybe clarify here that typically in HTML, when we talk about events, events bubble up the DOM. So yeah, if something happens at, say, a form element and you click submit, that submit button will bubble up the DOM through the form and through until something catches it and handles it. In this case, when an event happens in the Web3 tag, we actually want to push that down to the children. So when the children registered with that Web3 child event, the Web3 tag kept track of each of them, basically just in a list of child tags. And whenever any of these events happen, it explicitly iterates through the children that it has collected as they registered themselves and explicitly triggers these events on each of those elements. So the pertinent events are the Web3 ready event. So whenever a new Web3 object is injected, it will call this, trigger this event with the Web3 object. It should be noted that what this usually happens at the start, like during the initialization process of an application. It can happen again later if something were to change and there would be a reason that a new Web3 object were injected. In that event, all of the child tags will be notified about it again, and they will get the latest version of the Web3 object. The next thing is the Web3 account event. So anytime the Web3 element notices that the user has changed their account through MetaMask or through whatever tool they're using, it will emit a Web3 account event down to all of the child events so that they know what the current account is. Likewise, if the user changes the network, if they switch from mainnet to Kovan, it will emit a Web3 network event that will propagate down to each individual element that needs to know what the network is, so that they can adjust anything that they need to adjust based on that information. And things that they might need to adjust on the network are things like what contracts they're trying to talk to, but because contract deployments will change from network to network. Finally, the Web3 element will emit a block event whenever there is a new block. It doesn't give much information about the block. It just emits that there has been a new block. The primary reason for this, for the block event, is if there's something that wants, an element that wants to display information based on blockchain state. And my easiest go-to example of this is the ERC20 balance element that I've implemented. So the ERC20 balance element shows what the balance of a particular user for a particular token is. And that is a piece of information that could change at any block boundary. They could send tokens, they could receive tokens, or if it's something like embiggen, their balance could have potentially embiggened when that block happened. So rather than have each of these elements say, every 5 seconds I'm going to check my balance, or have each of these elements individually monitoring for new blocks and then checking their balance, the Web3 element monitors blocks for the entire application. And then when new blocks come along, things like the ERC20 balance checker can come along and say, hey, has my balance changed, without having to run extra queries to get that information when there hasn't even been a new block. So moving on from the Web3 tag, we're going to talk about the OR Web3 base class. So this is a base class for elements that require Web3. It is something that most of the rest of our custom elements are derived from. It emits and watches for the events from the Web3 tag. So it's going to fire that Web3 child tag as soon as it's inserted into the DOM, which is going to put it in the children list of the Web3 element. And then it is going to process all of the events that the Web3 element emits so that it can update the appropriate pieces of information. So the OR Web3 base class provides element.network. So on anything derived from this, you can just say element.network, and that will give you the network ID of the network that we're connected to, and that will automatically change without having to implement anything on this specific on your specific subclasses, because the base class takes care of it. So we have element.network, element.account, element.web3, and an element.onBlock function. So if you wanted to do something when a block happened, you could call element.onBlock, pass it a callback function, and every time a new block is emitted, or is mined, then that callback function will get invoked. So we're going to dig into the JavaScript code that implements the OR Web3 tag. So you can see here, if you're familiar with JavaScript, you'll recognize that this is ES 2016, which is a dialect of JavaScript that generally has to be compiled before it will run in a browser. But here we are importing LitElement from the Polymer LitElement project, or from the Polymer LitElement module. The LitElement class is the base class for our OR Web3 base class. So essentially all of the elements that we are creating, even the ones that aren't derived from OR Web3 base, are derived from the LitElement class. So we have to implement a constructor. The constructor is called as soon as this object is created and before it is inserted into the DOM. So if you need information that wouldn't be available until it was inserted into the DOM, you can't do it at the constructor phase. We'll talk about where you can do that a little later. But in the constructor, we need to call the parent class's constructor. In that case, that's going to be LitElements super. Until we do that, the variable this is not available. Then we are going to register event listeners for the Web3 Ready event, the Web3 account event, the Web3 network event, and all of those are just going to pass the event on to another function to record that. And then for the block event, we are going to iterate over all of the callbacks in this list of callbacks and call them with the event that was emitted here. We're going to define our list of block callbacks, which starts out as an empty list and will get appended to as subclasses of this call onBlock. Then we set up some promises that will resolve later once the account is ready and once the network is ready. So that was the constructor. Other parts of the initialization process. Here we have the ready function. So I mentioned that the constructor happens before the element is inserted into the DOM. The ready function is called as the element is inserted into the DOM. So by the time this function executes, the element has been inserted into the DOM, but it's not necessarily the case that everything has completed there. So in this case, we see the dispatch element, or sorry, the dispatch event where we're emitting the Web3 child. You'll see we have put that into a set timeout. What that means is it will run on the next event loop. We're not telling it that this is a timeout where we want to, say, wait 100 milliseconds. It's just run in the next event loop, but don't do this right now. That will ensure that the parent Web3 element has done everything it needs to do and is ready to listen for these events. If we don't put it in the timeout, on certain occasions, on certain browsers, we have found that the parent element is not yet listening for events. And so by sticking this into a set timeout, the listener is ready before the event gets dispatched. So we have the set Web3 function. This gets called when the set Web3 event is triggered. That will pull the Web3 element off of the event, or off of the event, the account, and the network, and it will also call a Web3 updated function. The Web3 updated function is a no-op in the base class, but it allows the subclasses to react to changes to the Web3 environment. There's also the set account function. So that's going to set the account based on the event, and it's going to resolve the account promise, so the account ready promise, so that anything that was previously waiting for the account to be ready now knows the account is ready and it can have access to it. Similarly, for network, we're going to pull the network off of the event, store it on the element, and then resolve the network ready promise. For all three of these, the Web3 ready, the set Web3, set account, and set network, we're going to trigger the Web3 updated function, which will just make sure that the subclasses are prepared to deal with any changes based on this information. So it gives them the opportunity to say, Web3 has changed, I need to do something. A few other functions that we have within the base class. So we have bind to value. If you're familiar with JavaScript frameworks like React and Polymer and AngularJS, a lot of those frameworks offer what they call two-way binding. So when you embed a piece of information into an element, you say you bound a property of a model to an input, for example, a number field. Anytime you change the number field through your JavaScript, it would reflect in your input. And anytime the user changed the number in the input, it would automatically translate back to your element. In LitElement, there is only native one-way binding. So if you store a piece of information on your element and change that through your JavaScript, it will automatically be reflected to what the user sees in the DOM. But if the user makes a change in the DOM, that doesn't automatically get reflected back to your element. So this bind to value is a way for us to explicitly say that we want to bind certain sub-elements to values of our of this element. And it also allows us to apply a transformation as we do that binding. So what this is going to do is we provide a selector, so that describes what sub-element within the element we've created are we going to bind to, and what property are we going to set when that value changes. So we go to this.shadowRoot. LitElement uses the shadow DOM, so this property is going to, or this element is going to have a shadow root property. Within the shadow DOM, we are going to query for the specified selector, and that will give us the object that we're looking, or the sub element that we're looking for, and we are going to add an event listener for when that changes. So anytime, like a form input or a slider or something like that changes, it's going to emit a change event, which we're going to capture here. And then we are going to apply any appropriate transformations to the value on that element after the change has occurred. And we are going to store that on the element property, the property name of that element. So that, and this will make more sense when I get on to a later example and we can actually see how this bind to value works. But basically, this means anytime a user makes a change within an element, it's automatically going to get stored back to the property. Here we have an onBlock function. So I mentioned earlier that elements can subscribe to block events. So anytime a block happens, they can get notified. They do that by calling the onBlock function and providing a callback. That callback function will be pushed onto a list, and we will emit an event that will propagate up to the Web3 element, saying that we want to subscribe to blocks. So it will start listening for blocks if it isn't already, and notify this element anytime a block occurs. And then, as we saw on the previous slide, or 2 slides ago, anytime a block event happens, we're going to iterate over our list and call that callback. In the event that we want to stop listening to callbacks, or stop invoking callbacks when blocks happen, we can implement we can call the clear block callbacks function, which will just set the list of callbacks to an empty list. That will mean we still get notified when new blocks happen, but we don't call any functions because our list of callback functions has been emptied. And then finally, the last thing that we have on our OR Web3 base class is the Web3 updated function, which here, as I mentioned earlier, is a no-op. This is something that subclasses can implement if they need to deal with the fact that the Web3 object has just changed. So having covered the Web3 element and the base class from which we will derive most of our other elements, does anybody have any questions?
Good so far.
Okay, so the next element we're going to take a look at is the OR Web3 account function. This is derived from the OR Web3 base class, and it just displays the account value. So in Ethereum, this is going to be your Ethereum address. Account is a slightly more generic term because it also covers addresses, but in Web3, or sorry, it also covers contract addresses, but in Web3, an account is, at this point, almost always going to be associated with a public-private key pair. So this is the entire account module. This is all we had to do in order to display the account. So here we import HTML from LitElement. We import our OR Web3 base class, and then we subclass the OR Web3 base class with our OR Web3 account. We create a static property called is, which we call OR-Web3-account. So this is going to be what you would put into the HTML to create an instance of this function, or an instance of this element. The name, strictly speaking, doesn't have to be a property of the element itself, but it makes it a little bit easier if you have that to refer back to. And the reason it's called is beyond me. That's just a convention that I found several people doing between Polymer and LitElement, was to name their tags and make those available as an is property. So then we have the render method, and the render method is where you handle the presentation. And in this case, it's very simple. We have an account property that will be passed into the render function, and using JavaScript string interpolation, we're going to put the account name into an HTML template, and we are going to return that. Now, this could be a much more complex HTML template. In this case, there's just one piece of information that we need to return, so there's not a whole lot to it. So yeah, here we have a render function where we return the account value, and we have a static property called properties, which returns a list of other properties, and anything that we list here, if that value changes, it is going to trigger a re-render of our template. So in this case, we're saying that account is a core property of this element, and if this property changes, then we need to re-render the content of our element. So very simply, since this derives from OR Web3 base, it is subscribing to the set Web3 account events. We don't have to do anything special there. That will automatically change the account property on this element, and then as soon as the account property on this element changes, that will trigger a re-render, which will cause the new account to appear on the user screen. So that's the extent of the accounts module. It'd be pretty simple. Does anybody have questions about this? Nope. Okay. So moving on to unit tests, basically all of the elements that we have so far have some degree of unit tests. We use Karma and Mocha to run the tests in the browsers. Karma is a framework that will fire up a browser or multiple browsers, run your tests, and report back through the command line. Mocha is a JavaScript testing framework that allows you to define your tests fairly easily. And using Karma and Mocha, we have a fairly consistent approach to unit testing across all of the widgets that we have implemented. So digging into the test suite, you can see here we import the necessary elements that we're trying to test. We have an element test utils library that provides some tools that make testing a little bit easier. In this case, we're going to use the get fake web3 function in order to get a web3 object that we can use for testing. Then we're using Chai for our assertions library. That's how we assert the things that the conditions that need to be met in order for tests to pass. So here, using Mocha, we have this describe function where basically we say we are going to be testing the OR Web3 account tag. This is just a description. It doesn't matter what you put here. Then it's going to call this function for testing. Before each individual unit tests, before it runs all of the unit tests, any of the unit tests, it's going to execute this before function where it's going to create a test area element that's just a div, and it's going to append that into the child. So that means, or into the body. So that means we have this test area element that we can stick stuff into so that we can test how it's rendering, and we know that's always going to be there. Before each individual unit test, we are going to come in and we are going to set the inner HTML of test area to an empty string, which means it will have no content and we can start fresh with our next test. So our first actual unit test here is a test of the OR Web3 account. So here we have our test area object that we created in the before function and cleared out in the before each function. So we're going to set its inner HTML equal to OR Web3. So we're creating our OR Web3 tag because the OR Web3 account tag is dependent on it. We've given that an ID of fixture that we can use to reference it. Then we create our OR Web3 account tag, and we give that an ID of test element. And that's basically it. We set this text to be the inner HTML of test area. And then we create our fake Web3 object. Using getElement by ID, we find our fixture. That's going to find this element. And dispatch a setWeb3 event so that we pass in the Web3 object that we want to use for this test. The unit tests, generally speaking, do not run in browsers that have injected Web3. They could potentially, but this is always going to override that injected Web3 with one specifically for the purposes of unit testing. Then once the account is ready, we don't want to run our tests until we know that the account is ready. We're going to request a re-render of the element, so we can actually request that the element is rendered again without having to modify any properties. We wait for that rendering to complete. Then we assert that the test element's inner HTML, the index of this string, and this string is the account name that the fake Web3 object we're using injects as the account. So we're going to search within the shadow root of our account element for this string. If that returns -1, it means it's not found, so something went wrong with the injection. We're going to assert that those values should not be equal. If they are equal, something has failed, and that means our unit test will fail. And then after we have executed all of our tests, we're going to run web3 current provider.stop, which will make sure that our current Web3 provider does not continue to pull for new blocks or anything else that may be going on that would potentially lead to memory leaks and things that we don't want to deal with within our unit tests. Normally, in a typical DApp, you start Web3 and you use it for the life of the DApp. But in the case of unit tests, we're creating a new Web3 object for each test, and we don't want the Web3 providers to continue running as we move on to the next test and have a new Web3 object. Any questions about the account element or any of the unit tests that or the unit test framework that I've just shown?
Good so far, man.
Next, we're going to talk briefly about the OR SRA tag. So this is derived from the OR Web3 tag. It injects the 0x standard relayer API information in addition to all of the Web3 information provided by the OR Web3 tag. For reference, when you hear me say SRA, that is short for standard relayer API. The OR SRA tag is configurable to different API endpoints. So while it defaults to pointing to api.openrelay.xyz, it can be pointed to any other OpenRelay instance if you were running a private instance of the open source OpenRelay. But you could also use it to point to any other relayer that implements a standard relayer API. So ERCDEX, Radar Relay, they all implement the standard relayer API. You could use these same tools to interface with them simply by setting the SRA property on your OR SRA tag to point to them instead of the default of OpenRelay. The ORSRA tag also allows you to specify a fee recipient. So we talked about our affiliates program in a previous series on Screenside chats. When an affiliate signs up for an affiliate account, they get a fee recipient address. All they need to do is specify that fee recipient address in the ORSRA tag, and any subsidiary elements that are children of the ORSRA tag will automatically know what fee recipient they need to use when interacting with whatever relayer they're talking to. Finally, the ORSRA tag will inject several network-specific 0x contract addresses. So contract addresses vary depending on what network you're connected to. So if you're connected to mainnet, you'll find the 0x exchange contract in one place. If you're connected to Covan, you'll find it in a different place. This will inject the 0x exchange contract address, the ZRX token contract address, and the WETH contract address, the wrapped ether contract address. At this point, it does not inject any of the token transfer proxy addresses, but those can actually be retrieved on chain from the exchange. So I'm debating whether, as we need that information, that should be provided by the ORSRA tag, or if it should be retrieved from the individual exchanges. And that's a determination I'll make at some point in the future. As an example of a child of the ORSRA tag, we have the ORSRA fee element, which gets fees from the standard relayer API target. Once it has gotten the fees from the target, it lets the user select the fee allocation. So within OpenRelay, we will tell the user, tell the application that we require, right now 0.2 ZRX as our fee. That this will let the user specify whether the maker is going to pay 0.2 ZRX or the taker is going to pay 0.2 ZRX, or anywhere in between as they split that fee. So the fee element, it starts out similarly to the account element. So we're deriving from the ORSRA base instead of the OR Web3 base. Again, we have our is static method that tells us our tag name, the ORSRA fee. Then we have our render function. Here in the render function, we see that there's three main values that we're interested in. There's one property just called value, one property called total fee, and one property called disabled. Assuming we have Web3, we're going to get the maker fee representation in decimal and the taker fee representation in decimal by taking this .maker fee, which is set elsewhere, and converting it from the base units to its decimal representation. So the base units is generally called Wei, and we're converting it to the same number of decimal units as Ether. So when we got the base fee from the standard relayer API, it would have been represented as an integer. But as we said, we want 0.2 ZRX. What that means is 1 unit of ZRX would be 10 to the 18th units of the base unit. So 2/10 of a ZRX would be 2 times 10 to the 17th units of the base unit of ZRX. Anyway, when we convert this to decimal, that means we will be showing the user that 0.2 ZRX instead of the 2 times 10 to the 17th ZRX. Likewise for the taker fee decimal. So yeah, here we're just converting that to what we want to show the user. And then here we have our HTML template. You can see that we're doing all inline styles. I would like to switch that to a separate style sheet, but I haven't bothered with that yet. So far, I've just been worried about getting something that was functional. We have a whole bunch of tickets for cleaning everything up and separating out styles and making things pretty. Right now, I've focused primarily on the functionality. So here we say maker and taker. We show the maker fee decimal and then the taker fee decimal. And then we have a range input that is disabled if disabled was set up here. It ranges from 0 to 100, and the value of this input corresponds to the value property of our fee element. So that's it for the template. To initialize our element, we have the constructor, which again is called when the element is initially created, but before it is injected into the DOM. We keep track of our last fee request, which at this point is going to be empty. We create a fee promise that will be resolved once we have gotten the fee from the standard relayer API. And we also set the initial value to 0. Then we have our ready function. Again, we have to call the super ready function. Once we have called the ready function, it's possible that total fee has been set as an attribute of our element. If that is the case, we want to keep track of the total fee that was provided by the application, and we put that into this initial total fee property. If no initial total fee was provided, then we just track initial total fee as none. Then down here, we look within our shadow DOM for our input. This is that range element that I mentioned a minute ago. And we add an event listener for input. Now, the input event basically means anytime the user drags that element the tiniest little bit, this event is going to fire, and we have an opportunity to handle that. When that happens, we are going to set the element's value equal to the input's value so that our element properly reflects the user moving that input back and forth. We're also going to monitor for a change event, and when that happens, we are going to emit a change event. Basically, the assumption here is that elements up the DOM from our fee element probably aren't going to care about every little input where the user drags the element back and forth and fires. The input event is going to fire 100 times. They're only going to be interested in the change event when the user lets go of the range slider and it indicates that this is their selection. Finally, we have a refresh fee function. So this is where we actually reach out to the standard relayer API and get what fee it wants us to put on this order. If we don't have Web3 yet, we don't want to try to execute this because we're dependent on having the Web3 function. This refresh fee function can be called in a number of different circumstances. And in some cases, it may be called before this.web3 has been set. If so, that's okay. It will be called again soon. And we don't want to worry about calling the function multiple times. So we're going to start out building the body for our post request. So this is the information we are going to post to the standard relayer API to ask what fees we should put on the order that we're getting ready to create. We keep track of whether we have changed any properties of the body up here, or if any of those have changed since the last time we made a fee request. Then we are going to iterate over this list of properties that would potentially impact whether or not our fees have changed. So we have the maker asset address. So that's going to be what token are we trying to trade. The taker asset address, which is what token are we looking to receive. The maker address, so this is who is making this order. And the fee recipient, which is who's going to get the money when this, or the fees when this order gets filled. So if any of the properties that we're iterating over are set, then we are going to add those properties to the body of our upcoming post request. If they are not set, we don't want to include them in the body. We just want those values to be empty when we send them off. If the key that we're iterating over is different than our last request, we set change equal to true. That basically means that something has changed since the last time that we did a fee lookup. So we want to make sure that the fees are correct given the new information. So this might change, like if in our maker widget as an example, the user can pick from a dropdown what the maker asset address and the taker asset address are going to be. As they change that information, that could potentially change what the fee structure is going to be. OpenRelay or another relayer could potentially say any orders for ZRX are going to be fee-free because we want to promote trading of ZRX. In those cases, it's possible that because the user changed their taker asset address from WETH to ZRX, then all of a sudden that's going to change the fees from 0.2 ZRX down to just 0 ZRX. So down here, once we've built the body that we're about to post, we keep track of that body in our last fee request. So next time this function gets called, last fee request will reflect the body that we're just about to send off. And if we found any changes since the last time, or we do not yet have a total fee, then we are going to make an AJAX request. The URL is going to be the standard relayer API that we are configured to talk to, plus v1/fees. So we're going to hit the fees endpoint on that standard relayer API implementation. It's going to be a post request, and we are going to provide our JSON, a JSON stringified version of the body object that we just built as the body to our post request. So that's going to go off to OpenRelay. OpenRelay is going to assess, okay, does this fee recipient have any discounts? Does this maker have any discounts? Do any of these, the tokens that are being traded have any discounts? And it's going to calculate what the fees should be for this order. It's going to send that back as a JSON string. We need to parse the result, and we're going to store that in fee body. So fee body.fee recipient is going to tell us what OpenRelay said the fee recipient should be. We're going to compare that to the fee recipient we already have. If those two values are different, something is a little off. So we are going to emit an SRA fee recipient event just to tell the application above us that these values are different. At this point, we don't have anything useful to do with that information that those things are different, but a particular application might be able to do something with that. You know, for example, they might be able to say, you know, oh, this fee recipient is not actually valid with this relayer, so maybe we need to connect to a different relayer. Maybe we need to use a different fee recipient address. But anyway, this event is there to let the application deal with that information. We pull the maker fee and the taker fee off of the object, converting them to big numbers because they come in as strings, and if we want to do math with them, they need to be big number objects. To get the total fee, we add the maker fee to the taker fee. And then to get the value is the percentage of the fee that the taker is going to pay. So we divide the taker fee by the total fee and then multiply by 100, and that gives us the taker's share of the fee. So if the taker's share of the fee is 0, then our slider is going to be all the way to the left. If the taker's share of the fee is 100, it's going to be all the way to the right. And we'll see what that looks like in a couple of slides when we actually look at this element. If the application developer provided us with an initial total fee, and that initial total fee is higher than the relay just told us our total fee needed to be, then we are going to use the application's version of the total fee instead of the relayer's version of the total fee. And that basically allows application developers to set higher prices so that they can collect a higher fee if they think their users will pay it. We're not going to enforce that they use the exact fee that OpenRelay said, but we're going to make sure that they are paying at least the fee that OpenRelay said. Here we call the resolve fee function. That's going to resolve the promise that tells any other parts of the application that the fee is ready to go. And we're going to emit a change, which is going to fire an event that other applications or other parts of the application can detect to see that a change has just happened. So here is the fee lookup element in action. So here's what it looks like embedded. It's within the ORSRA tag pointed at OpenRelay. The ORSRA fee tag, in this case, doesn't take any parameters. And then we have a slider here. So we have the maker on the top, the taker on the top, and then the maker's fee and the taker's fee. And then we can slide this back and forth. You can see right now we have some rendering issues that sooner or later I'm hoping somebody will take a look at the CSS and try and make this a little better. But basically, as soon as the element slides even just the tiniest bit, both the pieces on the left and the right update. That's because we were listening to that input event. And then as soon as I let go of the slider, it's going to emit that change event that would mean any other parts of the application that are paying attention to the fee lookup element get to see the value that the user just selected. That doesn't fire, every time I'm sliding back and forth like this, but as soon as I let go, that information becomes available to other parts of the application. Does anybody have any questions about the fee lookup element or questions related to what we've just gone over? All right. The final, excuse me, the final element that we're going to look at today is the OR Web3 sign element. So this is used to use Web3 to sign messages with the user's private keys. The messages will be provided as HTML attributes to the element, and then all the user has to do is click the button to sign. That will trigger the Web3 function, which will in turn sign the message. The use case here is within our maker widget, where a user can define an order that they want to submit to OpenRelay. They need to be able to sign that order. So the order's hash will be provided to the sign button as the message that it's going to sign. And then when the user clicks on the button, it will prompt them to sign the message. And then once they have signed it, it will emit an event back to the maker element so that that signed message can be sent off to OpenRelay to be listed in our order book. So here, again, we have a very simple template. It's just a button that gets disabled if there's no message. And the button just says sign. We need some internationalization here to be able to support this element in other languages, but right now it just says sign. So the signing process is a little bit more complicated than it probably needs to be, but that has to do with different Web3 clients behaving differently and doing some different things with respect to signatures. So within our ready function, this means that the element has been rendered and injected into the DOM. We are going to search for the button that the user is going to click. And when the user clicks it, we are going to run this function. The first thing that we're going to do within this function is call web3.eth.sign. We're going to sign this .message with the private key associated with this .account. So this is going to pop up a dialog for the user. they can either confirm that they want to sign this message or hit cancel saying, no, I don't want to sign this message. And then once they have made their choice, that will result in a callback to this function, which will either be an error, probably indicating that they chose not to sign it, or the result, which will be the signature. If we got an error, then we are going to dispatch an event with that error message that whatever is listening to the signing process can pick up on that error message and display it to the user or do something with that information. Assuming we didn't get an error, we're going to continue. The result here would have come back as a hexadecimal encoded string. We are going to convert that into a byte buffer. The signature that we get back from web3.eth.sign is going to be 65 bytes, and elliptic curve cryptography signatures consist of 3 mathematical elements designated as V, R, and S. This signature buffer that we get is going to have V as the 65th byte. Here we say 64 because it's 0 index, but it's the 65th byte. We're going to pull out V. Cryptographically, V is either going to be 0 or 1, but for reasons I'm not going to go into right now, the Ethereum blockchain refers to these as 27 and 28, decreasing them to 0 and 1 when doing the actual cryptographic operations. Some Ethereum clients, when they do the signature, will return V as 0 and 1, while other Web3 clients will return those values as either 27 or 28. So if we get a V value out of our signature and find that it is less than 27, we need to add 27 to it to get it from either 0 or 1 up to 27 or 28. And this is just one of several things that we have to do based on the fact that different Web3 clients sign things in slightly different manners. The next thing that we need to do is we need to find the R element, which is 256 bits or 32 bytes. So that's going to be bytes 0 through 32. And then S is going to be bytes 32 through 64. We convert our message into a buffer. And then the way you verify a signature using elliptic curve cryptography is you take the message that was signed and the 3 elements of the signature, V, R, and S, and you do some fancy math, and that will return the public key that was used to produce this signature for this message. If that public key corresponds to the current account, we have a match and we're good to go. We have found V and R and S for our signature. Now, there's another problem that means we actually have to check 4 different times to determine how exactly, what exactly the signature means. So the first problem is that some Web3 clients will return R as bytes 0 through 32 and S as bytes 32 through 64, while other Web3 clients will reverse that and return S as bytes 0 through 32 and R as bytes 32 through 64. So if we applied the recovery operations on our message given the signature and did not get the account we were expecting, then we have to try switching R and S and see if that gives us the right thing. If either of those give us the right thing, so if we got the right account in the first place, then we're going to dispatch a signature event given V, R, and S with signature type 2. The 0x exchange protocol accepts several different signature protocols. And if the message was simply signed and we get V, R, and S, then that corresponds to 0x's signature type 2. So we are going to provide V, R, and S with signature type 2. If R and S were switched, we're going to provide V, S, and R with signature type 2. The other possibility, and this is the case with more secure web clients, or Web3 clients, it won't have just signed the original message that we provided it. It will have prefixed it with a string that will guarantee that the message we are signing cannot be used as an Ethereum transaction directly, that we are just signing a message that confirms that we have signed it with our key, but it cannot be used as an Ethereum transaction. So if checking our message has failed on these first 2 attempts, then we check to see if the Web3 client signed a prefixed message. And again, we try with both VRS and with VSR, switching the R element and the S element. If either of these checks out, then we have a 0x signature type 3, which is the prefix signature. And once we have done this, we should have a valid signature. As far as I know, every Web3 client out there will fall into one of these 4 categories. And it's unfortunate that we have to do all of this work. Ideally, if all Web3 clients out there were consistent and all provided the same signature based on the same prefixed information, then all we would have to do here is sign the message up here, rearrange the bytes for the signature, and return that value. But instead, we have to do several cryptographic recovery attempts and return the value that we find. Fortunately, because 0xv2 supports multiple different signature types, we are able to do it off of a single signature from the user's perspective, whereas in older versions of 0x, it was possible that if we didn't anticipate that the message was going to be prefixed and the Web3 client prefixed it, we might actually have to ask the user to sign it again with the prefix or without the prefix, which could cause, a lot of problems and bad user experience. So at least this way, we only ever have to ask the user to sign things one time, and then we know exactly how their Web3 client works. So the Web3 signing element in action looks something like this. Again, we're within an OR Web3 tag because we need the Web3 client in order to handle the signature. We have our message here. I believe this is a Shoth or a Kekak 256 hash of the words "Hello World," although I may be mistaken. And then down here you can see the sign button. I'm not sure when I click this sign message if you're going to be able to see my MetaMask interface. No, it doesn't look like that's showing up on the Hangout. But on my screen, I see a MetaMask notification asking me if I want to sign this message. I click sign, and then the sign button emits an event that currently we're not doing anything to handle. But we could implement JavaScript using any framework that we like to handle that signature event. Does anybody have questions about message signing?
I'm good, man. Thank you.
All right. So far, we have the following functional widgets. We have the OR Web3 widget, which we talked about, the OR Web3 account, which we looked at, the OR Web3 sign, which we just looked at, the OR ERC20 balance, which will show the ERC20 token balance of a given user for a given token. We have the token select element, which will give the user a drop down of tokens that they can pick from a long list of tokens that I have compiled for both mainnet and for Kovan. So as the user switches between networks, the OR token select dropdown will automatically show tokens that are available on the network that the user is connected to. And then the OR SRA tag we looked we talked about. The OR SRA fee tag we talked about. And then the OR SRA maker tag we looked at in the previous Screenside chat to see what it looks like when a user can select a token, pick a price, pick the fees, and now with the sign button, they are able to sign that order and submit it back to OpenRelay. So all of those widgets are functional. I don't say they're complete because they're not pretty. There's a lot of things. They're not internationalized. There's a lot of work left to go into these widgets, and I'm hoping that we will get some community contributions to make these widgets look a little nicer, and maybe translate these widgets into some other languages. But right now, these widgets are functional and serve their purpose. In the near future, we're hoping to have a signed order widget that would represent an already existing signed order that maybe we've queried off of a standard relay or API instance. We want a widget for searching the order book and filtering through orders. We want a widget for setting token allowances. So in order to be able to trade tokens through 0x, you have to set an allowance for the 0x exchange to trade those tokens on your behalf. It'd be great to have a widget so users can do that in one click. We have market fill widgets that we want to develop that would allow users to take orders that they have found and submit them to the 0x exchange contract to fill one or more orders in a single go. Another concern is wrapped ether. So if you want to trade ether through 0x, you can't just trade it directly. You need to trade it as an ERC20 token. So there's this wrapped ether or WETH ERC20 token. It would be great to have a widget that allowed users to wrap and unwrap wrapped ether, or perhaps one widget for wrapping ether and one widget for unwrapping ether. And then another widget we've identified that would be useful is a depth chart that tells us, we have so many orders within OpenRelay at this particular price point, and just shows a graph of all of the different price points and how much ether we have, or how many tokens we have at each of those price points. If you are interested in contributing, check us out on GitHub. We have a number of issues open. Right now, they're posted on the wrong GitHub project, but they will be moved over probably by the time this video is posted. If you want to help with the functional implementation for the widgets that we haven't implemented yet, or the styling for widgets that have been implemented, documentation is going to be a big push. We want to make sure that we have documentation for how to use all of these elements. And then another thing that we're going to be looking for help with is translation, and making sure that our elements are as accessible as possible in as many languages as possible. So as far as next week goes on our Screenside chat, I am open to suggestions. I would like to do something a little bit less technical next week. I have a couple of ideas, but if anybody has suggestions, I am open to ideas. The last few Screenside chats have been very dense technically, so I'm looking for something that's maybe architecture diagrams and explaining how things work at a high level, rather than getting into doing code reviews. So if anybody has suggestions, I'll take them now or later. If anybody has questions, I'll take those now. All right, then. I thank you all for joining, and I will see you next week on Screenside Chats.